transformer here, and down here we've got a simulated domestic installation. Up here we're using an isolation transformer to separate our pretend system here from the 240 volt normal supply from the building. So that's what the isolation transformer is for. In the cable that goes down to here, we're not using the earth, we're only using the active and neutral to represent an active or a single phase feed from an overhead distribution line or from an underground service. So here at the transformer, we've got the transformer earth, so we've just knocked in a pretend earth stake. It doesn't go in very deep, so it's not totally accurate, but it should do what we want for this demo. Here we have, coming out of the isolation transformer, we've gone into a breakout box. The breakout box just lets us put a fuse in series with this whole thing, so I've got a 1 amp fuse in series with it. I've also got an AC ammeter which is measuring the current that will be flowing into our load. And here, so this is our transformer earth. Because this is an isolation transformer, there's actually no reference to earth on the two outputs, so they're just called live conductors. And so I'm going to pick one of those, which happens to be the black one here, and I'm going to earth one side of it, which means that is now the neutral at the transformer. So that's what we've got set up here. If I plug this in, the installation down there is all turned off. If I plug this in, I should have 240 volts here, so we'll just check that. So the 240 volts should be between the two outputs on here. So if I go between this terminal here, well, I can do it on the fuse. Let's go between the fuse here and the neutral, and I've got 247 volts. So that's representing our transformer that's producing the AC output voltage. And so now, to show you some of the things that can occur on an installation with the faults, we're going to take a walk down to the installation down here. Okay, so down here, this is simulating a domestic installation board, or like I say, it could be any installation really, but we're treating it as domestic. So what we have is we have our active and neutral coming down here from the transformer. That goes into another breakout box here, just simply so I can put an ammeter in. So this is measuring the current that's going into the supply. It's actually in series with the ammeter up the top. So it'll measure exactly the same current that one will. Now this is actually live all the way down here, so I've got to be a bit careful with what I touch. But these two cables here are representing my consumer main. So I'll just pull those out, just so you can see. So that's the active and neutral consumer main. You can see the active comes in and goes onto the top of the main switch, and the neutral comes in and goes to the main neutral link. So I'll plug these back in again. I've got my main switch off. I've got an RCD on my final sub-circuit, and I've also got a separate circuit breaker. So I'm using a separate RCD and circuit breaker so I can show you what happens when we simulate some of these faults. So at the moment that's all turned off. So if I turn this switch on here and energize it, I should be able to measure 240 volts at the input to my main board here. So we'll flick that on and we'll check that. So this is virtually the same reading that we should have got up the top there. So I'll just set the meter there so we can see that. Is that all right? And once again, I'll go between active and neutral here. So there's the neutral, there's the active, and you can see we've got 247 volts. There's no voltage drop in this cable because at the moment there's no current flowing. I'll give you a quick demo of the voltage drop in a minute, even though that's not what this exercise is about. In fact, I might show you that now. So if I flick on the main switch and the RCD and the load breaker, you can see the light's now on, the load's on. We've now got 220 milliamps of current flowing here on this meter. So that's showing you the load current, and you can see the voltage has dropped from what it was previously. I'll just turn it back off again. 247.6 volts, and it's dropped down to 238. So that's an example of voltage drop, and you can see without the load on there is no voltage drop. That'll be exactly what we're reading up the top. But like I said, That's not what we're trying to show you here today, but it's a good example so you can see anyway. So let's flick this back on again and we'll have a look at exactly what we're trying to prove with this setup. So this is all about indirect contact. Now what happens is the active comes in through the main switch. I've got it going through this RCD. That's a separate RCD. It's rated at 40 amps. It's only an RCD. It's got no circuit breaker in it and it's got a 30 milliamp trip. Then it comes out of the RCD and goes through this 4 amp circuit breaker. I picked a 4 amp circuit breaker because this is a couple of 100 milliamp load. It doesn't really matter. Normally that would be 16 or 20 amps if it's a typical circuit, or maybe 10. But for this exercise, 4 amps is fine. I haven't got a switch on the load, so really we'd have a switch so we could isolate this, turn it on and off. So I'll have to turn it on and off with the circuit breaker, but you can see that works okay. So that's the active, that's the final sub-circuit active going down to the load. This is the final sub-circuit neutral, comes back to our protected link. That goes back through the RCD, back onto the main link. And the most important thing that we're having a look at today here is this. This is our new MEN link right here. So that link joins our neutral with our earth. And you can see we've got our earth stake over here. So that's our main earth, which goes over into another stake that we've got driven into the ground. Very similar to the one up the top. Once again, they're not real earth stakes. They're not copper coated. They're just pieces of mild steel that I've banged into the ground. But it'll be perfect for what we want to show here today. The main earth comes in and goes next to the MEN link, which means you don't have to label it. So that's all good. And then over here, I've got the earth for the final sub-circuit. That goes down to this metal plate, which is just simulating the exposed metal of this appliance, whatever it is. Could be a toaster, could be a motor. And then I've also put a tap on here. So this tap would have an equal potential bonding conductor going to it. And so it should be at the same potential as this frame because they're joined together. All right, so let's have a look and see what happens under normal circumstances when we have a fault. So what I want to do now is I want to simulate an active to earth fault down here at the load. So this is all about fault loop impedance and you've been learning about it, so let's have a look at what happens. So I'll turn the breaker off so I don't give myself an electric shock. I'm going to plug in this conductor here into the active side there. I'll turn this back on, and what I'm going to do is I'm going to simulate the fault now by touching this onto the earth frame. Now because everything's in good order, what should happen is either the circuit breaker will trip because it's over 4 amps that's going to flow, or the RCD will trip because the leakage current will be over 30 milliamps. So whichever one of those is more rapid will trip. They might both trip if they're similar trip time. Let's have a look and see what happens. So you can see there what happened is the RCD has tripped, and that's protected the person from indirect contact. So if I actually have a hold of this and that fault occurred, then you can see that RCD has tripped within the 0.4 seconds, meaning that this piece of metal will not liven up and I won't get a shock from it. So that's protection by automatic disconnection, and it's the RCD that's actually done that. So what I want to show you now, so that's everything working normally. I'll just turn this main switch off. What I want to show you now is what happens if you lose your MEN link. So let's pull the MEN link out. So there's the MEN link. I'll put it there. Turn everything back on again. So you can see that the circuit's working as it was before. Everything seems okay, but we have this problem where we have no neutral to earth connection. And so let's have a look and see what happens this time when we have our short circuit to earth. Now there's every chance that the RCD will still trip, because RCDs do provide supplementary protection. If it does trip, then I'll bypass the RCD to take it out of the picture so you can see what happens. But let's see what happens. Look at that. Didn't trip. So I'm going to join that onto the earth metal there. And now, what you have here is an extremely dangerous situation where you've got a short from the active to this piece of metal, and the circuit breaker hasn't tripped and the RCD hasn't tripped. So there's no protection for somebody who comes along and grabs hold of that metal. So let's have a look and see what potential there is on that metal. So if I touch this meter here onto that piece of metal like that, and now here I am on the ground, so I'll just jab this meter into the ground here. And you can see, if I was standing on the ground here and I touched that, I'm going to get a touch voltage of 117 volts. Which means for a person that's got a typical impedance of about 1000 ohms, that's 117 milliamps, which means I'm dead. So that's why the MEN link is such a critical connection in the from AS3000, and that's why it's a critical fault in the capstone assessment if you get anything mixed up with the MEN link. Now that system that we're looking at here at the moment, see how the load still works perfectly well? So it looks like nothing's wrong. That system is actually called a direct earthing system, and the reason the breaker's not tripping or the RCD's not tripping is because the fault loop impedance is too high. So the actual resistance from here all the way back up to the transformer, that earth resistance is too high for the circuit breaker to trip. The closer you get to the earth stake, the lower the voltage is. That's because the earth stake, there's less resistance between this earth stake and the ground there, and so the voltage is less. The further away you get from the earth stake, the higher the voltage will be, until we get down to here where we get that 100 odd volts. That means that everything that's attached to this piece of metal where the fault's occurred will now liven up to a similar voltage, which means if I grab a hold of this earth stake, doesn't have a lot of voltage on it, but there's 10 volts from where I've jabbed this into the ground here to the earth stake. So there's potential difference between earth and this earth stake, which is a definite no-no. The other problem you've got, and this one's probably even more dangerous, is that you want to come and get a drink out of the tap. So here you are standing on the ground and you come and touch the tap and there's 120 volts on the tap. Totally dependent on the resistance between you and the ground, but you touch that tap and you're... Okay, so that's what happens without the MEN connection in. Let's turn that all off. I'm going to put the MEN link back in now. So we're putting it back to how it should be. And I'll just prove that it actually still works okay. And then I'm going to show you another very dangerous situation that can happen if you get the polarity wrong on the consumer mains. So this is back to normal now. I've still got my fault on here, so I'll just remove that fault for a moment, turn it back on. So you can see it's all working again properly. And if I touch this onto here, we should get our trip. So that's back working as we expect. Automatic disconnection of supply is working. Now, you're the electrician. You get called out to this place because the point of attachment's sparking or something in a storm or whatever, and so you pull the point of attachment off, which is simply removing the active and neutral. This could be at the pillar box or it could be at a point of attachment attached to the fascia. And you don't do a polarity test and you accidentally swap the active and neutral over and you stick it back in. So that's pretty simple to do. The worst thing that you can do now is not test it. If I test that, I'll find that error and I don't have a problem. But I haven't tested it, so I'm going to turn it back on. Now this time, remember, the MEN link is still in. We turn it on, and let's have a look and see what happens. I've got the main switch off here. So let's turn the load on. So that's working perfectly well. There's no problems, as far as we can see, except for this. Let's come and have a drink out of this tap and see what happens. So here we are on the ground, so we'll stick that back in there. We come and grab hold of this tap. and there's 125 volts on the tap. The reason for that is because the active is going straight onto the earth link, because we've got the active and neutral swapped around the wrong way, which means all the exposed metal in this installation is now alive at some potential above earth. If we go to the frame of our toaster, whatever this is, and grab a hold of it, 124 volts there. And if we go and touch the earth stake, not that we probably would, that's probably the least likely thing that you're going to touch. But because they're all joined together, there's 124 volts on the earth stake as well. Now this time the ME link is in. So that's the danger of doing an active to neutral polarity fault on the main. Let's just see what happens if we happen to have an active to earth fault as well. Let's see what happens if we touch this onto here. Now you probably already know what's going to happen. That still works because that's actually the neutral. So when I touch that onto there, that does have a problem, but we're not saying there's a fault here at this point in time. The fault is the electrician who got that active and neutral swapped around the wrong way. And you might be thinking, well, why doesn't the circuit breaker trip here? Or why doesn't the fuse up there blow? It's exactly the same reason as before. We're actually relying on the earth return, and so we could do some calculations. If I just flick that back on again, you can see that the current that we've got flowing in the loop, because we've got the active coming down here, going into our neutral, which is connected to earth, and the current's returning from here, back up through the ground, back up through the earth stake, back up at the transformer. And we're getting 15.7 milliamps. Now to do a calculation on that, we've got the load off. With the load on, of course, that's going to go off scale because it's more than 200 milliamps. But we're not interested in the load current at the moment. We're just interested in the fault current that's flowing because we've got the active virtually connected. It's like getting the active and sticking it in the ground. That's exactly what we've got happening. And if I measure the voltage here, using those two values, we can actually work out what the fault loop impedance is. So we'll do that calculation on paper for you later and show you what the actual fault loop impedance is. But 15 milliamps is not going to be tripping any fuse up there at the transformer very quickly, and it's not actually even getting a chance to flow through anything here. And if I turn the load on, I'll have to change this over to the amp scale. I'll just do that. If I turn the load on, that other current is still flowing, it's just not big enough to measure it.
Flick it to your 10.
Sorry?
Flick it to the 10.
It's just not big enough to measure it, but if I flick the load on, you can see there we've got the 230 milliamps. So it's probably about 240 odd milliamps altogether with the load connected. Once again, you can see the effect of the voltage drop with the load on. Turn the load off, we're up to 247, turn the load on, we're down to 237. We could actually work out how long that circuit is if we know what size conductors we got. I might even do that calculation as well, even though voltage drop's not really what we're